Let's bring in some concepts. The notes are already uploaded. This topic is going to be called energy balances. All right, so to give you a heads up of what's coming for this week, heat transfer is not different than your bank account. You put money in the bank account, you get money out of the bank account, right? If you leave your money there, you get some interest on it, and if you don't, you should. And every once in a while you check and you see how much money you have stored, right? Money in, money out, money generated through interest, money in the bank stored, right? Those four things are what we're going to be talking all about from now until the end of the class. Now, with a bank account, what I said is easy, but how do you make money in? Put the money, right? You have to have a job or something. Same way with heat transfer. How do you put the heat in? There are many different heat transfer mechanisms. Same way, how you get the money out is what you spend it. How you spend the heat, same things. How heat is generated is not through interest, but there are other mechanisms we will discuss briefly. And how it is stored for the case of material, for the case of heat transfer is very important, because in your bank account, you can put all kind of money from little to much and nothing changes. But if I put too much heat into water, it turns into vapor. And if I take out too much heat, it turns into ice, right? So there are some interesting things to discuss. Let's go about them step by step. And I'm going to start with a very basic concept that you should know. That is the concept of control volume. Right? And what is a control volume? So in space, we have this imaginary surface, right? It's a closed imaginary surface. You have all these notes already uploaded. And all it does is divide. Inside, is it this big enough for you guys? Way up in the, okay. So I promise I'll make bigger letters. The semester is starting and gotta get warmed up. Okay, so it's a closed imaginary surface. All it does is divide inside from outside, and it must be closed because otherwise inside and outside would mix up, right? So you have mass coming in and mass coming out. You have heat coming in and heat coming out. So if you have no mass exchange, we call it a closed system. The surface is always closed, but we call it a closed system when we don't have mass coming in or coming out. For example, if I put water in a tank and I heat the tank, right? I put water in a tank, close the tank, heat the tank. Okay, better. Get your gallon of milk, put it in the freezer, in the fridge. It's going to cool down, right? You didn't put milk, you didn't take out milk while it's cooling down. That's a closed system. Quite cool. Those are easy. If we have no heat exchange, we don't study them. No. Those are called adiabatic systems. By exchange, I mean across the control volume. For example, I can make a control volume that has something hot and something cold inside. There will be heat transfer within our control volume, but it's not exchanging with the outside. And that is the case of a heat exchanger. A heat exchanger is actually an open system, but ideally the heat exchanger should not exchange heat with the environment. It's just between the two fluids. All right. The control volume can move in time, can stretch, can do lots of things. And we're going to be using this very much. So this simple dashed line I put here means a lot. And typically we do it with the dashed line to represent the control volume. You will be doing a control volume in your exams. Not only the first quiz, but in everything afterwards. Okay, so let's talk about now energy balances. Well, first of all, the energy balance is always associated to a control volume. So I'm about to write an equation, the first equation of the term. Will be many. But before you do that, you have to have a control volume. Otherwise, it's like talking about money without saying if it is his account or her account. What makes any sense out of that, right? We're just money. So the first equation is our bank account of heat transfer. Q in all right, I explained this in detail in the notes uploaded, but what we have is Q in, heat coming in, heat coming out, heat generated, heat stored. Q is thermal energy, and the units are joules. And notation matters. So this is big Q. You're going to see small q is something else. So we have put the book put quite a bit of thought, and we are putting quite a bit of thought. And for the most part, we stick to the notation in the book. So thermal energy. You guys already had thermodynamics? Okay, what is the other name for thermal energy? Enthalpy, right? Enthalpy. I'm not going to go crazy with entropies or anything like that. But enthalpy, you got to know. All right. So let's talk about each one at a time. In and out can be by convection, conduction, radiation. All these words I'm sure you heard before. I'm going to assume you never did, right? But these are the mechanisms bringing in. This is what is your job to bring money in. This is what's your fancy to spend your money out, right? Q generated, that is associated to other physics like joule heating or things that happen inside, like frictional heating. Lots of very interesting things that actually matter and are very relevant technologically. For now, I'm going to give it to you. I'm not going to ask you how much heat I'm generating with so many amps in a wire, right? Although it's very easy, but I'm not going to burden you with that. I want to focus now on the heat stored. So heat stored between points 1 and 2, right? You have to say, again, it's no different than talking about money. If I say, you made so much money, was it in a month or in a year? For example, when I talk about salaries, in my native Argentina, that's where the good accent comes from, People assume you're talking about monthly. Here, if you talk about salaries, people assume annually, right? So in heat transfer, whatever it is, we better know what it is, right? So between 1 and 2, whether that is a month, a year, or a millisecond. And this is so you probably have been using, what symbol have you been using in thermal for enthalpy? H or I? H, okay. So there is something funny in the book. Sometimes they use H, but the problem with H is that it's also a heat transfer coefficient. So to avoid confusion, we're using I. That is, mechanical engineers use I, right? So this is enthalpy, specific. Sorry for the small letter here. I is and this is in joules per kilogram, right? Mass is in kilogram. And we get Q in the units we needed to have it. So what we have at the end minus what we have at the beginning. Look at this cool equation, because this equation accounts for mass balances too, right? So do not ever, I'm going to write few, if any, complicated equations, maybe never. But don't ever be fooled by the simplicity of equations. What I wrote here, that looks like trivial. It's a huge thing to say, right? This equation accounts for changes in temperature, for example, and changes in mass. This equation tells you that how you lose heat by losing mass, or you gain heat by gaining mass, or all kind of things. Specific heat is going to be in theory. I'm not teaching you anything new here, but at least we go step by step. Now, you might have heard about CP and CV, right? Depending on whether the heat transfer is happening at constant pressure or constant volume. Now, I'm not going to worry about that. I'm going to call it C. For most of this class, we're going to be dealing with fluids that behave in an incompressible way, including air. If we don't worry about compressibility issues, CP and CV are the same. I'm going to call them C. And it's just the derivative of enthalpy with temperature. And since it is incompressible, there's no point in saying if it is constant pressure or constant volume. Right? What would be the units of C? What would be the units? Kilogram. Yeah, joules per degree and mass, right? Because enthalpy was already per unit mass. So I used to put a lot of emphasis in unit conversion in the past. That make me any new friends doing that. But let me tell you something that is important. If I tell you it's 20 degrees, and it's 20 degrees C, it's awesome. If it is 20 degrees Kelvin, you better get a good jacket, right? Okay, but if I say my specific heat is 400 joules per kilogram Kelvin, or if I were to say 400 joules per kilogram degree C, are those two numbers the same or not? They are the same. And this is a super important thing. We use the same, this is the same symbol, the K or the degree C, for the absolute temperature or for the variations of temperature. So for absolute temperature, 1 Kelvin is not the same as 1 degree C. It's not the same as 1 degree Fahrenheit. For absolute temperature, all those are all different. But if I'm going to talk about a variation, so for example, if I if I go from 20 degrees to 22 degrees, I increase 2 degrees, right? Some amount of heat or whatever. But if I go from 293 degrees to 213 degrees, right? It's the same thing. Sorry, 293 degrees to 295 is 2 Kelvin, right? And those 2 Kelvin are the same as 2 Celsius. So when we're talking about variations or derivatives, Kelvin and Celsius can be exchanged. It's a crazy thing. We use the same symbol for 2 different things. One is how much money you have in the bank. The other is how much money you have changed. It's not quite the same concept. You can make money or you can lose money doing some things, and whatever was there is something different. So this is the same as joule per degree centigrade kilogram. Same thing.